Good day, everybody. So this is something I've been meaning to do for a while. And back in 2012, when I was still teaching a basic class for Zeiss, I had a student record a video of me writing a program. Was just me going through lesson 3 of my standard basic class. And that video has become a little bit dated. It's had quite a few views. A lot of you probably have viewed that video. And I've always thought to go back and remake the video using a modern version of the software. So I figured I'd do that this morning. So here we are. We have lesson 3 from the basic class. This is just writing a simple program of using a 1, 2, 3 block. So this is the program I'm going to create. I'm going to create a simple base alignment. And then I'm going to go in and basically solve these 10 challenges that are given right here. This is also first chance for me to play around with Calypso 2023. It's not really what I've been using lately. So let's give it a look. So here we are, Calypso 2023. Nice new interface. Looks like they've started to settle down the icons. I like to see the stoplight up here. In fact, for those that like to maximize their screen, it looks like we can turn the stoplight on and off. Without further ado, let's get right to our program. So we're going to create a new measurement plan. I'm just going to start by loading a CAD model. I'm going to go right to the desktop. I have 1, 2, 3 blocks step file. I'm going to open that up. And of course, the first thing I'm going to do is do a save as once that comes in. And there it is, converting the step file. Very nice. So let's do a file, save as, and we're going to call this 1, 2, 3 block V1. Always like to put that V number at the end of my program so that things can auto things. So we brought in our CAD model. Of course, what you'll notice immediately is that this is a spline model with the seams going up the sides of the bores, not a true analytical or geometric model. So let's go ahead and heal. We're going to come up here. There's our new icon, a little band-aid. Go ahead and click all of the items on healing, and that happened pretty quick. Looks good. Okay, going to hit save. Save early, saved often, as they say. Let's go ahead and write our program. Now we see we have a new toolbox that opens up on the right. There's always been a toolbox in Calypso. It just now is docked and automatically opens. We're going to use the extract features function. I'm going to go ahead and pull datum A off the top. That's going to be plane 1. And then let's go ahead and grab plane or cylinder B right here. And then we're going to grab plane C over on the right. I'm going to go ahead and rename those real quick. Back plane A. And we're going to call that cylinder B. And plane C. Nowadays, when I'm writing a program, I like to go ahead and put things into a group. So we'll form that up into a group, F2, and we're going to call this our alignment group. Alignment group. Let's capitalize that. There we are. There's our alignment. Now, when I'm doing alignments nowadays, I like to go ahead and use some constructions so that we don't have any uncertainty or projection errors. Let's just go ahead and grab those real quick. So I'm going to go construction, intersection, and let's go ahead and first we're going to go with the intersection of A and B, and we'll just call that intersection AB. That's going to give me this point right there that I can use as an origin. And we'll just copy paste that. We'll open this up, and instead of plane A, we're now going to grab plane C, and we're going to call this intersection AC. And that gives us this line over here to work with for planar alignment. Okay, so I'm going to go ahead and throw those into a construction group, form group, F2, rename, construction group. Excellent. There we are. I'm going to leave the icons large just for easy viewing. I normally would turn that off and go to the small icons just for easy working with. Like I said, I'll leave those large for now. Let's go ahead and create our base alignment. We're going to go in, base alignment, create new base alignment using the standard method. I'm going to go ahead and come here, select already extracted features. I'm going to grab plane A for my spatial and my Z origin. I'm going to come over here, I'm going to grab intersection AC, that's going to be my planar alignment. I'm going to grab intersection AB, and I'm going to use that as my XY origin. Now I have absolute certainty about where my origins are coming from. Of course, we're going to do automatic alignment, and we always want to set that base alignment to 0. Those are the default settings. So we'll click OK. So looking pretty good. We got our simulation active. Let's go ahead and go back and finish our program. So we're going to come in here to my clearance planes from CAD model. I'm going to go ahead and use a 20 millimeter offset. Looks pretty good. And click OK. Update clearance plane features, define features. I'm going to say yes. It does want to change that plane C, but I don't actually want that to change. So let's go ahead and make sure it's using the CP plus Z. Now everything looks good to me. Click OK. And we are good to go. Let's go into our features. Let's take a quick look at our lesson since that's what we're actually trying to do. We have established our base alignment. Next, we want to get the location, the X value, Y value, size, diameter of the hole in the back left corner. You'll notice that I actually haven't done anything with the strategy yet, so let's just make sure that our strategies look pretty good here. We're just going to zoom right in. Of course, my computer lagging just a little bit with all that simulation going on. I guess I could turn off the machine itself for a minute and just work in space. Anyways, here we are. Let's look at this strategy. That strategy does look pretty good. Maybe I want to do a little bit different strategy in there. I could always delete my polyline and pop out a quick uh, grid. So let's just drop a grid in there real quick. Going to open that up. Looks like it's already trying to go back and forth a little bit. Of course, when we're working with a grid, we want to use the distance function. I'm going to go ahead and say that we're going to stay 2 millimeters away from the edges. That's going to give us a nice back and forth. Oh yeah, that looks great. We can set this to 100. Oof, no, that's going to be a lot of back and forth. So this one should be what? 1, 2, 3, 4. So let's try that. 4. Oh, look at that. It's cleaned up perfectly. We got a nice little grid that's going to go back and forth in between everything that's on there. And other than that, let's go ahead and go with a step width. Typical step width is going to be a maximum of 0.25 millimeters while scanning. Basically, we're going to use our filters with a 2.5 millimeter wavelength on the filter. We need to have 7 points per wavelength for the filter to activate properly. At 0.25 step width, that actually gives us a total of 10 points per 2.5 millimeters. That way, when outlier elimination activates, it won't mess up our filter. So we can click OK there, click OK here. I'm going to drop into evaluation real quick and show you what I'm talking about. We're going to turn on our outlier elimination. When we do outlier elimination, when we're scanning, we want to include 5 adjacent points. This is per the Zeiss cookbook. And since this is a linear strategy, we're going to go from 0 to 10. It's pretty easy to remember what these pre-filter settings are. If it's the second block, then we fill the second field, and that is wavelength, length for linear stuff, linear filter, lambda C actually. Other here, undulations per revolution. Revolution is for round stuff. If it's the first checkbox, we fill in the first box. I'll cover that again in a second when we do the strategy or filters for the cylinder. Click OK. Looks good. For filters, I'm just going to turn them on. We're going to use a spline low pass filter. Drop in real quick. We're not going to mess with anything here. Of course, per the Zeiss cookbook, we might mess with stuff. The Zeiss cookbook says to use a Gauss filter. However, for linear strategies, I do recommend a spline filter. It does handle the end of the data a little bit better. This is not a lesson about filters, so I'm just giving you basic filter information. Next, we're going to go ahead and work on our datum B cylinder. This is actually a threaded hole with a 5/16 18 thread. So I'm going to quickly switch us over to inches because I currently have the system in metric. So feature settings editor, and we're going to come in here, units, length unit from millimeters to inches. Click OK. I can now see up on my stoplight that I'm clearly in inch mode. And let's go ahead and work on our cylinder. Going to come into the strategy. We have a circle path with 3 sections that came in via my default strategy. I'm going to drop in a helix. Of course, we're going to come over here to the start. We're going to go formula, and this is going to be a 5/16 18 thread. So I'm going to go 1 divided by 18 to get my pitch. Yeah. Click OK. And there's our pitch, 0.055555555, repeating. Now, I actually want to put this in the center of our cylinder. So we can see that our cylinder is currently at a depth of -383 with a length of 383. The middle is going to be about 190. So I'm actually going to take and go in here, formula, and then I want it to be starting at 190, but we're actually going to go 0.190 minus, and then a parenthesis, and then over here. And so that's going to be the 190 is again going to be the center of the thread right here, half of 383. If I wanted to be super exact, right, I could go minus 1915. And I'm not going to go any further decimals. You guys get the idea. And we click OK. I've now moved the start here. I want to take this value, right? So I can go formula, and I can actually take this value, Control C, and then go OK. And now I want to do the positive thread, right? So this is the start height, and I want to scroll upwards. So now we're going to go to the target height. We're going to go to formula. I'm going to paste that formula in, but instead of a minus, I'm going to go with a plus. And now we're going to go OK. And so now we have a higher value. I'm going to go ahead and convert both of these to input fields. I do that just in case somebody runs the program in metric. These will then properly convert. If I leave them as formulas, they'll of course always be inch numbers. And of course we see a very nice 2-rotation helix right there in the middle of our threaded cylinder. Let's go ahead and set our number of points here. We're going to take 500 points. Oh, sorry, 2 rotations. Let's do 1,000 points. And our speed is automatically set based on tolerance, but we are good. So we'll click there. 198. Seems a little slow. I'd have to look it up in the cookbook real quick, which I do not have handy. So I'm just going to click OK and accept that. Click that as OK. I'm actually going to go ahead and set my outlier elimination while I'm here. So let's open this up. We're going to turn on outlier elimination. Once again, we're going to include adjacent points to the total of 5. Here, because it's a rotational or circular object, we're going to use undulations per revolution. The warning told us that this only was usable on a rotational or round object, circular, cylindrical. And now we're going to do our pre-filter. Of course, because it's the first box here, we're going to put it, the number 10, in the first box. Again, real easy to remember. If I'm using the first radio button, I put it in the first pull down field, a 10. If I'm using the second radio button, I put the 10 in the second field. The first one is for rotational, revolution. The second one is wavelength, linear objects. Easy to remember. Always use 5, always use adjacent, always stay with plus or minus 3 standard deviations, except in special cases. Oh, I should also turn on the filter while I'm at that. So let's come here. Filter is now on. Again, standard rotational filter, UPR 50. Click OK, and we're done there. Now, for plane C, we're going to go ahead and do a quick couple things. Again, delete that polyline. I'm going to activate the -X stylus. And then I'm going to, again, go ahead and use just a grid. We'll open that grid up. I do like the up and down pattern. Let's see if we can get it to go in between all of these holes. There's 5 holes. So 1, 2, 3, 4, 5, 6 is my number in that axis. So let's go ahead and go with 6. Yep, that seems to drop in quite nicely. Always go to distance. I'm going to stay 80 thou from the edge to avoid anything funny happening. I am using the -5 stylus. My step width, 0.25. 590 speed is fine for that. Again, I'm just going to use the speed as recommended by the cookbook. And yeah, looking pretty good. Click OK. Let's go ahead and take care of our outlier elimination and filters. Well, we've already set that on plane A, so I'm just going to grab the paintbrush. I want my evaluation settings. I'm going to come down here to plane C, click OK, and if I show you real quick, you can see that yes, we did transfer all of those filter and outlier settings. Click OK, click OK. So looking pretty good. We have our entire that was when I had the wrong tool set up down here. We have our entire base alignment programmed. Let's go ahead and run that base alignment just to make sure that everything is good to go. So I'm going to come down to the run button. I'm going to go ahead and clear existing results. I want to go from the feature list. I want to use clearance planes. My run mode is going to be normal. I'm going to reduce my speed to 160. If I was on a real machine, I would turn down the knob. We're going to do a manual alignment, and everything else looks good here. Some new settings, close plan after CNC run. That's a new setting from Zeiss. That's interesting. Let's hit start. There we can see our Calypso timer, and let's go ahead and take some probing. So looks like tip number 1 is active, and 2, there we are. So we've taken our first 4 manual probings. I'm going to click OK. It's a little bit more challenging. I'm going to measure a cylinder. So we'll take 4 probings at the bottom. 1, 2, 3. Oh, a little bit of an angle, hard to see. 4, and then we'll go to the top. 5, 6, 7, and 8 manual probings. I'm going to click OK to finish that feature. And finally, it wants me to measure plane C. 1. We see the correct tip going in, a nice validation for the program. It's kind of why I like to do this. I know it seems a little funny to run a manual alignment in simulation, but it does properly test our manual alignment. Click OK, and let's watch it run. There it goes. Running our program. I do have speed set to max. For what it's worth, it is doing real-time collision detection. So when you're doing an actual simulation of your program, I recommend that you turn the speed down to half or lower, much lower if you have a slow computer, maybe the slowest speed. That's going to give you the most accurate collision detection. Okay, so that will be important if you're trying to use the simulation for collision detection. And this program seems to be running quite nicely. Yep, there it is. Now I'm scanning the sides. Oh yeah, look at that. I do like having the simulation. I created the stylus using the stylus system creator. One of the important things, if you want your machine to actually show in the simulation, you have to pick a machine size that Calypso has available. Maybe in another video I'll show how to set up Planner, and I'll show you how to determine what that is. When we first run a program, this information on run pops up. This is not an error. This is not an error window. Notice it says information on run, and it says no features available for report. I didn't program any characteristics, so a little bit of a misnomer on the wording. Thank you, Zeiss. Anyways, all I'm going to do is uncheck display at CNC end, so this window never pops up again for this program, and close. Of course, measurement plan being the proper term, but we all call them programs anyways. Let's take a look back at our lesson plan. Let's do what we're going to do. We're going to measure the X value, Y value, and diameter of the hole at the back left center on top, and then we're going to do the perpendicularity front center to the primary datum plane. Let's start with lesson 1. XY value diameter. So we'll come back to Calypso. I'm going to activate tip number 1, and we're going to go ahead and switch to, now there's a couple funny things we can do here. If I actually look at my lesson plan, you'll notice that I actually need a circle here, here, and here. I also need one over here, and I'm going to use my intersection in the center. I'll need a cylinder up front. That's going to be called cylinder 1. So if I plan this out, rather than doing this lesson in a linear fashion, which is what I show in the other video. Remember, this is a redo, modern techniques and all. What I'm going to actually do is program all the cylinders, convert them into circles, and do everything in one shot. So let's do that instead. I already know that I want this first one to be called cylinder 1, and then these are actually going to be 2, 3, 4, and 6. So I'm going to come down here, extract features. I'm going to grab this one first so that it's actually called cylinder 1. Then I'm going to grab the other ones I want. 1, 2, 3, and then I'm going to grab I could do something fancy with a recall feature points over here. I think I will, just to keep the lesson succinct and kind of show a little technique. And then we're going to come over here. So now we have these cylinders 2 through 6 that I actually want to be circles. Very tricky, huh? Very tricky. So we're going to come back here. We're going to come to Plan, Advanced, Convert Cylinder to Circles. When we measure a cylinder as a circle, we should always put the circle at 50% up the axis of the cylinder. This is the position that best emulates the perpendicular constrained location of the bore, and so when we measure a circle, that's the best place to measure. I've highlighted 2 through 6. I click OK. Those are now all converted to circles. I'm actually going to go ahead and just come up here, Edit, Replace. I'm going to look for the word cylinder. So cylinder. I'm going to replace it with the word circle. Of course, it helps when you spell it right. Circle. There we are. And let's go ahead and replace. I hit once. There we are. Boom. And we'll replace all. Notice that replace all only replaces all within the highlighted area. I'm going to hit close. And if I bump back to my lesson real quick, we'll see that this was actually 2, 3, 4, 5, and then that was number 1. So I was off. Oh, I was off by 1 in those namings, wasn't I? I hate things to be confusing, so I'm just going to rename this one to circle 1. Go down. Rename this to circle 5. That way everything lines up with the lesson when I'm done, for the most part. Over here, now that this is going to be called circle 1, I actually don't want to remeasure it, so I'm going to do a recall feature point. So let's come here, recall feature points, uncheck recalculate nominal geometry prior to selecting my cylinder B, which is where I'm actually getting my data from. Click OK. Circle 1, I now have the information inside. Click OK. Oh, actually, while I was here, I could have taken care of my filters and outliers real quick. So turn on my filter, come to outlier elimination, include adjacent points, 5 adjacent points, undulations per revolution because it's a circle, 10 to 5,000 per my pre-filter setting. Click OK, click OK. And there we go. So now I've actually created all the circles I need for the rest of the top of the part here, and I can just sort of march through the lesson. It wants me to go to select already extracted features, give out the X and Y of that back right corner, right? X value, Y value, diameter, hole on top. That one there, called circle 2, called circle 2. I'm just going to open it up. X. Let's set our tolerance to 10 thou minus 10 thou. And I want to use last input so that it'll just remember that each time. Now I have 10 thou, and for diameter, 10 thou. Everything looking pretty good. While I'm here, I'm going to go ahead and optimize the strategy for measuring this. You remember before we had it as a cylinder. Now we have a nice circle strategy in there with one strategy. For number of points, 500, 0 to 380. That speed looks pretty good. Let's go ahead and go with it and click OK. Again, I would just look in the Zeiss cookbook. Generally, you see it giving me pretty good speeds by default, so I'm going to stay with those. Calypso 2023, pretty much shining along the way here. Oh, I should be using some of these functions on the right here. I'll try to utilize that toolbar a little more. Let's click OK. And once again, I'm going to come to my Format Painter, Evaluation Settings, and I want to apply the filter to all the circles. Click OK. Now all my circles are filtered. You know what? I like to put my features into groups as well. So I'm just going to go ahead and right-click, Form Group, F2. This is actually my 2mm star group. Click OK. Boom. So now we have a nice set of groups starting to form over here. And on our characteristics side, we've created our initial characteristics. In fact, I can just call this F2. If I wanted to do anything, oops, cancel, sorry. Right click, group, F2, and then I could call this whatever, challenge 1 group. Boom, challenge 1 group. Okay, so what are we doing next? We have perpendicularity of a cylinder on the front and center. I've got 2 Cartesian hole-to-hole distances along the left side and a simple distance xy between the hole in the front center and back left corner. So we're going to basically go with perpendicularity of this cylinder, distance here, then distance here, then we're going to do the distance across here, and then we're going to do the angle between a line constructed here and a line constructed here. That'll basically take us to halfway through the lesson plan. Let's do this. Okay, so first is perpendicularity. Let's come over. Ooh, look at this fancy stuff. Position check, GDT perpendicularity. Going to open up that perpendicularity, and this is already selected. So let's grab my cylinder and my datum and remind myself of the tolerance, 1 thou, tight tolerance. So let's just go ahead and go 0.01, done. Nice. What do we got here? If I want a projected tolerance zone, I could add that in. Ooh, error. Thank you, Calypso. And if I want MMC, I can see that here. No modifier. Projected. No, it's giving me an error. Anyways, this is what we're going to get. Oh, look at it. New little symbols. Nice new layout to Calypso 2023. Add rotations and offsets. Oh, kind of cool. I like what's going on here. Again, next, we're going to go ahead and do the 2 Cartesian hole-to-hole distances. So the lesson says to use Cartesian distance. Nowadays, I would probably prefer to use a caliper distance rather than a Cartesian distance. So the lesson does say Cartesian distance. I could just open that up real quick, and then I can do something simple like 1. Oops. Select already extracted. There's circle 1. There's circle 2. Enters the tolerance, everything I need. I don't need additional datums. I can go copy, paste, come in here, and change circle 2 to circle 4. Now I have the distance over here, so I've gotten my 2 Cartesian distances in pretty easily like that. Like I said, nowadays, if I'm going to do a distance like that, I would actually prefer to have done it with a caliper distance, which you see is basically going to give me the same ease of use. Here it's giving me the outer tangential automatically, and it's giving me the distance between them automatically. Notice I can get x and y out of this one. So caliper distance, not dissimilar to simple distance. Let's just go ahead and delete that. Okay, next I was going to output simple distance xy front to back. Here I am going to go ahead and again, distance, it wants us to use a simple distance. I probably would output a caliper distance with the modern tools that are available to me in Calypso, but there's my two features. Mind you, of course, I can always click on the list and pick it from the list. I just prefer clicking on the CAD when possible. And of course, I want to output the X and Y values, so I can put those there. I can actually relabel this to X and Y. Very simple. Okay, so let's come back over here. Next, angle between features. Oh, so we need some 3D lines. So we're going to come up to features, 3D line, quick talk. 2D lines are physically measured. They're a plane with no width. A 3D line is an axis. Use it for constructions and such. So let's go ahead and open that up. And I'm first going to do a recall. And I'm going to recall, if I remember right, it's circle 2. Yep. Circle 3 and circle 4. That forms the first of my 2D lines. Click OK. Click OK. Control C, Control V, copy paste, open that back up. Notice I can hit the strategy button. It takes me right to here. Now I want to go with 4. Going to hold the Control key on my keyboard. Circle 1 and circle 5. Notice I grabbed those in order to establish the vector, and then we'll click OK. The order you select creates the order of the 3D line. So my 3D line starts here. Notice the values minus y 1.1, x minus 0.6. So we can see via our coordinate system that that's where we're located. And we, of course, see our line going. So let me go ahead and unrender this so you can see the constructions that we're actually making. Probably make it easier. Click OK. I now have my two 3D lines. I like to keep things neat. I'm going to drop those into my construction group up here. And let's go ahead and go back to my characteristics. That's all looking pretty good. And now I want to go to size, angle, angle between features. I'm going to open that up. Feature 1 is 3D line 1. I'm just going to do the simple thing, Control C, Control V, backspace, type a 2, hit enter. My second line is in there. What's the nominal I'm looking for? I'm actually looking for 28.6 degrees. So this is not 28.6 degrees. There it is, 28.6. Quick explanation. It looks like when we look at this small picture that would be the small angle between here and here. And we look at this big picture, it seems like it would be this bigger angle over here. These represent the direction of our vectors. So if you remember, my first line, 3D line 1, was constructed between circle 2, 3, and 4. It's moving in this direction. It's moving in the minus y direction. So its positive vector goes in this minus y. I actually can look here, hit enter, and we see our minus y space axis on that line. See its origin up here shown by the trihedron, and then we see its direction of travel. Click OK. Now for 3D line 2, of course, that one we constructed from here going off to the right, so it's going to go from 4 to 1 to 5, and its vector is off in that direction. Now, if we consider the positive direct vector ends, so right here, if we look at this, I have a positive vector here and a positive vector here, and so the relationship from this positive to this positive seems like it would be this huge angle, right? But in fact, according to Calypso, this one is that huge angle. And it's actually this positive to this positive. See, positive to positive, positive to positive. Now over here, when I look at the little picture, I actually see that I'm going from a positive to a negative. So now on here, I'm going from a positive to a negative, and we're actually measuring this angle. We can't see it, of course, but it's, over here in space if we extended this positive line and this negative line, and that gives us there. So that's a super detailed explanation of what's going on with Calypso angles. And of course, you won't hear it anywhere else. Here we are. Oh, I still have simulation on for the machine. It doesn't matter for programming purposes. Just zoom out, take a moment to drool over that beautiful new contura, and then let's zoom right back in. Okay, next lesson. Let's come here. So we've completed through number 5. And now we're on to 6. The overall width and length using symmetry points. Oh, super easy stuff, of course. I'm going to render real quick. There we are. And again, I like to be exact to the lesson. So it does say width and length. So first off, let's do our width. We're going to switch here. Define points, not define a space point. That'll create single points as a single feature, not edge points. That's a special sheet metal tool. Define points, and then we're going to go ahead and I think I'm going to go left. I'm going to change my rotation point real quick. Define rotation point, put it on my block. Notice that my zoom zoomed to the whole machine. So I'm going to turn off the machine for a minute. I'm going to turn off the probe for a minute. And now when I hit zoom to extents, I get a little bit better zoom and we see everything rotating on my screen. Again, right click, define rotation point. Okay, looking pretty good. Let's go ahead and take care of that next lesson. So overall length, symmetry points. Define a point, come in, we're going to go left, right, and then OK. Yep, generate. So let's take a moment to read this here. New generation of several clearance data in feature, question mark, and then a comment. This may be necessary for detour generation as outside feature uses different styli. If yes, if you, the user, answer yes, then a clearance plane is generated for every probing point or strategy segment that you created. If you, the user, answer no, then you have to manually make sure that the navigation is collision-free by setting things like intermediate points or additional clearance planes on yourself. Clearance planes that you have already programmed are retained when you answer no. So by answering yes, it'll put a probing or a clearance in between everything. By answering no, whatever you did is kept. I didn't do anything special for clearance, so I'm going to say yes. Okay, we can go ahead and open that up. And if we come in here, we see that, yes, we have a clearance data in between our additional probing points. So it's going to go clearance plane, probing point, clearance plane, probing point. While I have this open, I like to recenter my symmetry points to each other. So I'm going to double click, and I'm just going to make that a 0 and a 0 for XY, a 0 and a 0 for XY. I leave this at +1 inch, -1 inch in Z. Notice that's the feature coordinate system, element coordinate system. Click OK, and we now see that nicely. Click OK. Let's go ahead and create our other symmetry point. One on the front, one on the back. Click OK, answer yes, open that up. Notice that now my nominals are a little off, so let's put that on 0. Let's put that at -0.2, so it's exactly where my 1 was on the sides. Come to our strategy, double click, set those to zeros. Notice the Z is at 1 and -1.5. Click OK, OK. Let's come back up here. Now we can do our distance. Notice that the nominal is off because the last thing I did was an angle, so set it back to 0.01 minus 0.01. Down arrow, checkbox, click OK, and now we have our next two characteristics done. Let's go ahead and move on. We have our overall true position of the 5 holes with MMC on the right side of the block. Oh yeah, no problem. We're going to do these holes on the right side of the block. Let's go ahead and activate the -X stylus, and then we're once again going to do the fancy conversion thing, extract feature, extract that cylinder, come up here, and we're going to rename it, plan, advanced, convert cylinders to circles, just that one, okay, and I'm going to open it up. What are we going to name this one? Whoops. It's currently cylinder 2. It's actually going to be circle, we're going to call this 6. Sorry, there we go. And looking good. Okay, so we got that right in the middle, right where I want it. Everything's looking good. And next, let's go ahead and make sure that our strategy looks good. Yep, looking good right out of the gate. Thank you, Calypso. Let's set our evaluation setting. I'm just going to come up to a different circle, format paint, evaluation settings. Boom, we now have that. And now I'm ready to create my linear pattern. So options, and there it is, pattern. I'm going to create a 1D linear pattern. What is my offset? Does it say? No, but I think that it is 550. Yeah, there's the Y value at 1.1. It's half of that number. It should be listed here. Old lesson. Anyways, let's go ahead and type in that offset, 0.55, and we have 5 holes. That's a real number. Notice that they're going off to the right. That's because I've set this with a space axis Z, so it's going to actually go off in the XZ direction per the A1 angle. Instead, I want to set this to use the plus Y axis. Nope, that's not looking good. Maybe I want to use the plus X axis. Hey, there we go. Everything seems to drop into place. Click OK. Now, if I wanted to skip a hole, by the way, I can use my exclude index to skip a couple holes. Click OK. Click OK. And there we go. By the way, nowhere near 20 minutes on this video. Sorry, but it is what it is. Hopefully this is good information for everybody. Now we actually want to turn that into a true position. So I'm just going to come up here with MMC. So let's go ahead and create our diameters first. Now you notice I can just click the checkbox for position right here and enter my tolerance, which is going to be 14 thou. 0.014. I don't normally use this. I would normally just go up and create it from the menus. Personal choice. Come in here. I do now have this true position. Notice that they have a loop in them, which is super handy for getting all of the values out of there. So now this is actually diameter circle 6. There's my sizes. I can come in here and I see that I have my base alignment, everything set up. I can do a couple different things. One, I can just plug in my datums directly, A, B, C. And so that's just going to put the features in directly. That'll give me one value. If I go ahead and put my constructions in, so I actually put my intersection AB and my intersection AC in, this will be more exactly, I know, where the calculations are coming from. If I look at the output of the X and Y, they will calculate by hand to be the correct values I want, but the actual values themselves will not change. So this or putting the features in will give me the same value because Calypso does actually work off perpendicular constructions. It works off intersections, not perpendicular intersections when it's doing alignments. Now, personally, when I'm going to go in and do something like this, I like to do something a little bit different. So I'm actually going to create an alignment. So we're going to come to Resources, Utilities, Alignment. I like to keep my alignments at the top of the stack. I'm going to open that up. Now I'm going to put in my actual datums. So we're going to put plane A. I'm going to put in the intersection AB. Yeah. Oops, sorry, I didn't mean intersection AB. I meant intersection AC right there. XY origin is intersection AB, intersection AB, and then Z origin is plane A. So now it's just the base alignment, right? I'm going to make a comment, alignment ABC, click OK, click OK, and now I'm going to come down here and I'm just going to replace this with alignment ABC. So now I have this distinct alignment I've created with alignment ABC. It says it's alignment ABC. Everything is super clear. All three of those methods will give me the exact same output. I like to do it this way because if I'm going to show something to a customer, I can open this up. I can clearly discuss the datum reference frame. I'm going to create all the datum reference frames that are used throughout my drawing so that I can go through and talk to the customer about what datum reference frames exist. If I have to do things like best fits, offsets, rotations, constraints, I can control all of those within the sub-alignment itself. And then as I go through all of my GD&T, because I've created all these alignments, I can quickly apply them here. Now, this is a Bohr pattern, so rather than output 6 individual true positions, I'm going to switch this to a Bohr pattern calculation. It says delete true position tolerance. Yes. All that means is I have to now come back, reset my datums, come into this button, select the features that I'm looking for. In this case, that's going to be circles 6, item 1 through 5. I could select the entire thing here. I can select the individuals here. I generally do the individuals, just a habit. Click OK. Now, there is no best fitting in this alignment because we have ABC as a fully constrained datum reference frame. So I'm going to uncheck translation, uncheck rotation. Notice how when I uncheck rotation, these come up, which is why I don't do it rotation, then I'd have to check 2 times. So easier to uncheck translation than rotation. Now, what best fit method? I'm just going to stay with Gauss. Gauss. Now, if I do want to do a minimum zone, that's going to be a Chebyshev or an outer tangential calculation for my best fit. So least squares best fit, well, Gaussian least squares best fit. Chebyshev least squares best fit, which is still an outer tangential. View tolerance, which is basically going to try and account for the MMC of the datum. So if you do have MMC on your datums, this is what you're going to use. And L1 is going to try to make as many holes as possible, as good as possible. L1 is always a funny math. Click OK. And we now have everything set up. We do need MMC. There we are. And create, adapt evaluation to existing characteristics. Click OK and OK. I don't need double characteristics. If I go in here, we'll see that nothing was actually changed. And OK. Okay, so there we are. And I'm going to hit save real quick. I've got my position in with a Bohr pattern. Oh, you know what? Let's just add in a plot. I'm going to guess that 100 is the right plot number for magnification. And let's finish this lesson up. We have our overall thickness, C value, profile, flatness. I do have the overall thickness here because we do have our -x stylus active. So let's just come in here and we can take a little bit of a plane. I'm going to do something tricky though. I normally would just do a space point, right? Space point, in, out. We open it up, we change the clearance to be a +x, and we output the z value. So that's going to be per the lesson. Now, if I wanted to do something a little more advanced, I could go extract features. I can grab the plane off the bottom. Now, this gets a little trickier. I'm going to go to my strategy, open up my polyline. I'm going to delete the current polyline strategy. I only have limited reach with my current stylus. So I think I can get to about there and then there. And let's go ahead and come over to here, and here. So I think that that's just a nice little bit across there. I maybe could get across there too, but maybe I have a post here. So I'm just going to go around the edge. Speed 236 is fine. Step width 10 thou is what I want. Remember 0.25 or 10 thou. Click OK, click OK. I'm going to rename this just for my convenience. Plane bottom. Now I'm going to come up here to construction, and I'm going to get the maximum coordinate, construction, minimum coordinate. I'm going to go back in, grab my plane. There's plane bottom, that's why I renamed it. Relative to, now this is always a weird one. The actual feature, if the actual feature is at an angle, then we're going to get our data relative to the feature itself. So axial to the calculated feature. So usually when you want a maximum coordinate, you actually want it relative to the nominal feature because the nominal feature is constrained to the base alignment. So relative to the base alignment, I want to know what is the maximum and minimum point on this surface. That's, of course, approximately a -1 inch nominal. Oops, minus, not 0.1, but -1. There we are. Whoa, 10,000. What am I doing? There we are. Okay, -1, type a point. Now, a point versus a 3D point. A point is, of course, always going to be compensated along the cardinal axis. So again, I want the maximum point as if I had a micrometer. So I want to use a point, not a space point, which could, of course, could be at a slight angle due to geometry stuffs. Click OK. Come down here. We're going to do the same thing. This is just our minimum coordinate. So we have our plane bottom. Boom. We want to go nominal feature. We want to go ahead and set this to -1. Oops, I forgot to output my nominals, so we're going to go checkbox, up, checkbox, OK. And we now have a min and a max coordinate. We also have an average value. By the way, this average value should be somewhere between my min and max. If it's too much closer to my min or too much closer to my max, then I know that there is something funny going on with my data, my measurement, my part. Somewhere, ask questions. Sometimes that's why we want to get multiple outputs, is because the differences in the multiple outputs hint to us that there is a problem. Next, we're going to take a look at profile using the backside of the block and then flatness of the top plane real quick. So let's go ahead and activate our, let's use our -y stylus since we're on the back of the block. There we are. Come over here. I'm going to extract that feature. Boom. Let's open that up. And oh yeah, there we are. Now here's a funny thing. I went ahead and used a cool grid over here. I wonder if I can use that same grid over on this next one. So if I come up to plane C and then highlight this, I'm going to transfer both the evaluation settings and the measurement strategy down here. Click OK. Let's open this up. Let's call this plane back so I know which plane it is. The transfer of the strategy didn't come out necessarily exactly what I was looking for, but it's still going to save me some time and effort here. So right off the bat, I see I want to rotate my grid, and that means that I need to change my numbers around. There's actually going to be 1, 2, 3, 4 sections. Oh yeah, look at that, looking good. Let's go ahead and bump this back up to 10 so we get nice to the edge. I could even go with a big number, 100, but it doesn't matter on this one. So 10, looking good. I like that. Back and forth, meanders. I'm actually going to do it as a series of lines. Yeah, that looks great. And I'm going to click OK. And then I'm going to copy paste. I'm going to take the second grid. I'm going to unrotate it. And now my number is going to be 2. And let's leave this back at 10. So now I've created a complete box. It's going to go 4 vertical lines, 2 horizontal lines to give me a nice thorough definition of that surface for the purpose of profile calculation. Let's click OK. And then quickly we're going to come over here to, oh, let's use our toolbox. Yeah, let's come over here. Where is that going to be? We got form. There's profile. Oh, I think I just double click. Yeah, it drops it right into my characteristic list. I think once I get used to the toolbox, it's going to speed things up. I kind of wish it was on the left side. Can I dock it to the left? No. Right click? No. Nothing happening? No. No. Maybe. Maybe there's settings for it. Anyways, that's that. Let's come in here. I'm going to grab my feature, which is going to be the plane on the back. And now my primary datum, if I come and look at this, it's actually going to be profile to ABC. So let's just grab our datum reference frame, ABC. See how easy that is? Oh, I should have looked at the tolerance. 5/10. So let's go ahead and set that to 5/10. 5. Now, bilateral one result is going to take the maximum value and go times 2. That's generally used for SPC purposes more than anything. I'm going to go ahead and go with bilateral 2 results, so I do get my minimum and maximum value. Notice if I want to do the most correct version of profile, I would do outwards to infinity and inwards to infinity as 2 separate characteristics, which would give me my, of course, maximum in space and maximum in material values, which is most correct per the ASME Y14.5. But we're just going to do this because it gives us a quick min-max and looks good. Profile done. Let's come back here. Last thing is flatness on top. So once again, we're just going to come up here, to our new toolbox and grab our flatness. Interesting, there's GD&T flatness, and flatness ref. So let's see what GD&T flatness says versus flatness ref. So GD&T flatness. We go here. I'm going to grab plane A. Restricted portion. So that means that there can be an area where we only use part of the surface. Neat stuff. Okay, so let's go ahead and set our tolerance. I believe that is 1/10. Oh yeah. 0.0001. Let's set up our plot. This is going to be a pretty fine surface, so let's use 500. And hit close and OK. So now what is regular flatness? Okay, regular flatness is just traditional flatness as we've seen it in the past. That's weird. That was a weird little bug there. I wonder what it was going to do. Not sure. And then, of course, flatness ref is if we have to do flatness per inch or something like that. So we go OK. I typically output only the maximum zone. We're going to enter our tolerance, 0.0001, enter. Oops. And we're going to input our parameter. We're going to use a zone size of 1 inch by 1 inch with a 90% overlap. We're going to limit the angle between adjacent planes to 5 degrees. And I do want to reference the plane in each zone for true local flatness. So there we are, 3 types of flatness real quick. And with that, we have completed all 10 items in our lesson. Let's go ahead and hit save, and let's run our program. Came up here. We don't need to do a manual alignment again, so we're just going to grab the 1, 2, 3 block alignment. Boom, boom, boom. Everything else looks good. Hit start. And let's zoom in and watch. Let's go ahead and turn on the tracing. Of course, I can follow the stylus. We can see if there's any collisions by opening this little panel up. We are running at maximum speed. I generally say if it looks slow, it is slow. So I definitely could speed up the scan for plane A. Of course, we are going to do a pretty tight flatness evaluation. Yeah, these are all nice conservative speeds. When you go to speed up a measurement plan, what I generally do is start increasing the speed by If it's looking real slow, I might double the speed. Otherwise, I increase by 50% during the current level. But here's what you do, is you run the program or run the feature and look at the standard deviation and the form, okay? And as you increase the speed, when those change by a factor that you care about, typically 1/10 of your tolerance, that's when you've hit the maximum speed you want to go. See, you want to go as fast as you can go before your speed starts to actually alter your result. So go slow, see what the slow conservative speed result is, then start doubling or 50% increases in speed until you start to see the form and standard deviation change by 1/10 of your tolerance, at which point also looking at the result. Like if it's a diameter, you want to see if the diameter changes. If it's a location, you want to see if the location changes. By whatever you're measuring changes by 1/10 of the tolerance plus standard deviation plus form. And if you get all of that right, then we would be maximizing our speed. Ooh, look at that. That's a little funky move, huh? Ah. Didn't show as a collision, so probably just a little animation stuff. See, our program's running about 2 minutes. Measuring those holes on the side. Now, in reality, I think if some of the holes on the side were threaded and some weren't, they would be two different callouts, actually. But I would probably just run a Helix in there. Here we are getting that data off the bottom. Of course, we can be watching our features, so we see the features themselves execute. I see that I need to do a little organization to finish my program up before it's done, and then we will call it done. So we'll let it finish running here, and then we'll neaten those things up. And there it is, doing that strategy across the back. Let's go ahead and finish organizing our program properly, though. So we'll go ahead and drop these features in here. Let's go ahead and move the constructions up to here. And when I go to my program, we're going to do that. And actually put those here. Oh yeah, that's nice. Okay, so we're going to go cylinder, 3D object, down to 2D object circles, 3D object plane, and then our 1D or 2D objects with some points. So that makes for a nice, neat organization. Here's the plane on the back side. Ooh, if I was thinking this through, there's probably a better order. So actually, let's go with that. And that. Oh, that's nice. So now it'll do the circles. It'll grab the point on the bottom. Remember, that is, in fact, point. Bottom, just as a reminder. And then we have our symmetry point for width. And length. So yeah, looking nice. Now I like to have the constructions at the end of my program. This is so that anything in a construction, when it calls for a feature, doesn't cause my program to run out of order. So by putting the constructions at the end. By the way, I didn't optimize this for time efficiency. This is optimized for easy for me to read the program, easy for me to follow. Also, when I have my customer in, this very simple organization to my program makes everything neat and easy for the customer to follow. I might even go in and do things like further annotate. So, if I wanted this to be clear, I could call it 0.325 and then give it an underscore. And then I can highlight that, Control C, down arrow, Control V, down arrow, Control V. I'm going to turn off my simulation real quick, by the way. That's the system definitely bogs down when it has that active. Anyways, let's come down here. Oh yeah, much quicker. Control V, Control V, Control V. And here, we're going to call this instead Control V. And then this is going to be the circle on the plus X side. So that'll just be a quick, easy reminder for me. And so now I've got all the stuff in the program labeled, the entire feature set, 3D line, right? I could even call this 3D line left and 3D line angle. Simple names, just to remind me what they are. Max coordinate, bottom, min coordinate, bottom, right? Simple, simple organization. Come over here. Let's go ahead and organize now. I started off with this challenge one. Oh, man, did you see me misspell that too? Nice. Thank you, Calypso. Challenge. Is that right? Is there an E on the end? Challenge. Oh, man. You know what? Let's just call this item. One group. And let's just call this instead our result group. I think that'll be better anyways. There we go. Click OK. Open it up. Drop everything in. Now, if I was creating a true program for a customer, I would actually just come to the end of each of these. And so like X value, circle, blah, blah, blah. See, by renaming it, it says 325. So I actually would have done something like X value, circle, 0.325. And then I would put the zone in. So it might be zone A-3, page 1. So A31, and then I would just go through and rename everything. Also, as far as groups go, I usually will create like a front view group, a right view group, section A, section B. Those are how I do the groups. And as I mentioned before, I'll typically turn off the large icons. So that's all looking good. Let's quickly set up some PyWeb on our measurement plan. So we're going to go to a couple things. We're going to go to Resources. We're going to go to Results to File. We're going to turn on the table file. We could also set it to CNC Start. I'm going to turn on a PDF copy, and I'm going to save my measurement points. And I always set this up to a big number like 5,000, and then we'll hit OK. Now, it doesn't matter anymore, but I still, just by habit, will come in here. I always set this to all characteristics and like program. And then we leave that. If I wanted to turn on Excel output, I would do that here. Simply click there, grab my characteristic XLT, go OK. And now I'm going to come into my multi-printout. I currently have a PyWeb standard protocol. Going to turn on the stuffs. We're going to exchange the row template. We're going to add plots and report. And over here, display plots and report. I'm going to set that to on, on. Oh yeah, that looks great. Magnification of plots. Oops, I forgot to set it on those flatnesses. Let's set that to 500 as well. That looks pretty good. And then under report, additional report for my true position. Let's go ahead and turn that on, but I'm going to leave it off for the other functions here. Yeah, I think that'll do everything I need. Click OK. We've quickly set up our PyWeb report. Now, I could also, if I was proving out a program, I could very quickly add in a trend protocol. So actually, let's just go here, new PyWeb reporting, and then we'll come here and I'll do a trend protocol, select, and looks pretty good. Same thing, exchange, and we turn these on, and display plots is turned on. Magnification should already be set, and then report, additional report, already turned on as well. So all looking good. I've now saved my PyWeb. And rather than rerun the program, because I do have data in all my features, I'm going to do something interesting. I had ran the program without turning on to save measured points, so I'm just going to save my measured points real quick, saved under part number 2, and we're going to go to Plan, Subsequent Evaluation, several measurements and alternate paths, just like we're used to. Grab that measured points that I just took. Everything looks good. I do want to output Excel this time so I can test it. Click OK. This down a little. Hoorah! There we are, everybody. There is our 10 challenge lesson in Calypso. Once again, we went ahead and did the old lesson 3, whose video you see elsewhere on my channel. This was a modern, updated look at it using Calypso 2023, really my first look and playing with Calypso 2023. Again, we can turn on and off the stoplight. We got the cool toolbox. Hope you found this lesson helpful. Like, subscribe. We'll do occasional videos. Thank you very much, and good day. This has been John Feuerhelm